Hey everybody, it's Mr. Larrabee. This is week 6. It's our asynchronous notes. We last covered the second derivative test in class, and we're going to do more of it here today to give you some further background in the second derivative test and how to explicitly use it. In the first part here, on part A, we're actually going to start reviewing and looking at the first derivative and what we actually get from that. So you're going to be able to compare what we get from the first derivative compared to what we get with the second derivative. So in part A, it's saying, hey, let's use some calculus. Let's find out where our critical points are. And we should remember that our critical points are wherever your derivative is equal to 0. Or it could be when the derivative is undefined, but in this case, we're looking at a polynomial and there's no undefined corners where the derivative would be, or breaks in your graph. So going ahead to find our derivative, we're going to use the power rule to get minus 3x squared plus 6x. And if I want to find out where that's equal to 0, I'm going to want to factor out a common factor. It doesn't have to be the greatest common factor, but I'm going to factor out a 3x from both. That'll leave me with a negative x plus 2. So here now I have my two factors, and I can apply my zero product property by setting 3x equal to 0, which would just give me x equals 0 as a solution. And then minus x plus 2 equal to 0, which is going to give me x equals positive 2. For my other critical point. And we can see that on the graph at 0 and 2, we're looking at this point here, which is a valley. It's a minimum, relative minimum. And then at 2, this is a relative maximum. We're just using that visual over there to confirm our results. Part B, find the exact coordinates. You know how much I love using Desmos to take the grunt work out of computations. So to find the exact coordinates, what you're really doing is you're just plugging in the critical point into your function, so f of 0 and f of 2, to find out what your output is. And I actually did this in Desmos right here. So here's my function. I created a table and I inputted 0 and 2. My outputs are negative 2 and 2. So I'm going to have negative 2 and 2. So my coordinates are 0, comma, negative 2, and 2, comma, 2. And sure enough, that matches on the graph. That's exactly where those maxes and mins are. If I were to ask you what is give me a relative minimum, you would say negative 2, because that is relatively the lowest point around the valley that I'm looking at when x is equal to 0. You wouldn't give me the x coordinate, just the y. All right, so part C, this is called the first derivative test. It's not explicitly put out here. This is the first derivative test. I can spell. All right. So we could look at the graph and just determine when it's going up and going down, but using calculus and not just looking at a graph is a different tool. So what we want to do is we want to create a sign chart, because the first derivative tells us whether something is increasing or decreasing. We have two critical points at 0 and 2. So once again, just a reminder, this is the first derivative. And I'm going to test points for the first derivative to the left of 0. So perhaps I pick negative 1. I'm going to pick something between 0 and 2, easy to pick, 1. And then I'm going to pick something to the right of 2, and I'll pick 3. So I'm really just looking for signs of these values, whether they're positive or negative, to say whether they're increasing or decreasing. And yes, I also created a table for this. So here we are, negative 1 and 1 are my inputs. So I'm going to get my outputs for the derivative will be negative 9, 3, and negative 9. So negative 9, 3, and negative 9. And once again, I plugged these inputs into my derivative because I'm trying to find out where I'm decreasing. So that's a negative value. That means decreasing. Positive value. So that's going to be increasing. Negative value. So that's going to be decreasing. And where am I going to be increasing? Increasing is just going to be between 0 and 2. Okay, and this is an open interval because it's not increasing or decreasing at 0 and 2. The derivative is 0. For decreasing, it's going to be negative infinity all the way up until 0. And then also, this is the union symbol, meaning I'm including both of these intervals from 2 forever to the right, positive infinity. Okay, so the first derivative test tells us where things are increasing and decreasing, and we can take it a step further by saying that indeed at 0, this is going to be where I have a relative min, because the sign changes from negative to positive, and that will be your reasoning. And at 2, I would have a relative max, because the sign of the derivative changes from positive to negative. I'm increasing and then changing to decreasing. So the first derivative test is useful for finding mins and maxes and determining behavior of a function. For the second derivative test now, keeping in mind that the first derivative was minus 3x squared plus 6x. So I know that the first derivative is equal to minus 3x squared plus 6x. So the second derivative will be using the power rule once again on the first derivative to get minus 6x plus 6. And when I set the second derivative equal to 0, what I'm getting here are possible inflection points. I'm emphasizing possible because there's one other thing we have to check. We also have to check if there is a sign change for your second derivative. And if there's a sign change, then there is an inflection point. That means something changes or the original function changes its shape from either concave up to concave down or concave down to concave up. So solving this, I can subtract a 6 and then divide by negative 6 to get x equals 1. So here I have a possible inflection point. Now I need to do the same thing I did with the first derivative test and put my possible inflection point on my chart. And emphasize this is the second derivative chart. So I'm going to be evaluating second derivatives in these regions to see whether they're positive or negative. So I'm going to try 0 and 2. And sure enough, I know it's easy to plug into the equation, but I use Desmos once again to save some time, especially for the video. So here is my second derivative. And I plug in 0 and I get 6, and I plug in 2 and I get negative 6. So this will be positive 6 and this will be negative 6. So here I have positive values, which means I'm going to be concave up, I'm going to be holding water, and concave down, I'll be dumping water. That's how I like to refer to it because that's what it looks like. So because you do change concavity at x equals 1, there is an inflection point because the sign of the second derivative changes. All right, always, sometimes, never. Let's switch it up here. If we know that the first derivative at 2 equals 0, okay, then there has to be a relative extrema when x equals 2. All right, so what do we know about when a first derivative equals 0? Well, that could be, it's a candidate, right? That's just a candidate for relative extrema. If there is a corner, well, that wouldn't be it. Well, if there's a corner, the derivative doesn't exist. But if it equals 0, it could be a relative extrema, which means maybe it could be something like this or something like this. But it could be the squiggly guy here too, where somewhere in the middle we have a derivative of 0, but the derivative doesn't change sign. The derivative is positive, and the derivative is still positive afterwards. So it doesn't have to be. Could it be? Yes, the derivative, first derivative could change sign. It could go from positive to negative, or it could go from negative to positive. And that would indicate that there's going to be a relative extrema at that input. So I'm going to say this is sometimes. All right, for the second one, once again, we know the derivative at 2 is 0, the first derivative. The second derivative is also 0 at that point. Then there is a relative max when x equals 2. This is tricky because if the only time that, if I'm looking at these examples right here, here I have derivative of 0, derivative of 0, derivative of 0. The only time that I would also have a second derivative equal to 0 is when there is a possible inflection point. But I don't know enough about, like, for this one right here, the one on the far left, this is concave down and then still is concave down. The second one, concave up and still concave up. It doesn't change. And that's where relatives and maximums occur. So this one's a never. This one doesn't work. If the first derivative is 0 at 2, once again, same starting point. And then the second derivative is negative. Okay, so here now we got a different situation. Right now we know there's a critical point. And we know this is going to be, because the second derivative is negative, this is going to be concave down. So if I make something that's concave down, like this, and there's a critical point, so a derivative of 0 somewhere, that point has to be a maximum. There's no other way around it. If the derivative was positive, it would be flipped upwards, and then it would be a minimum. So this one is always. All right, last section here. This is a little drawing. I don't want to say challenge, but it's a drawing exercise. So here I'm going to have the derivative. First derivative is positive. That means I'm increasing. Okay, increasing. Second derivative greater than 0. That means I'm going to be concave up. I'm shorthanding here. So increasing and concave up, that's going to look like this. I'm going up and I'm going to be holding water. So I encourage you guys to all try this. Like, pause the video for the others and try to draw some kind of curve that satisfies the conditions. So for the second one here, we have a decreasing function, so it's going down, but it also has to have a second derivative greater than 0, which means it's still positive, which means it's concave up. We're holding water, but we're decreasing. So here we're decreasing and we're concave down. So decreasing concave down would be like this. Second to last here, we have an increasing function because the first derivative is greater than 0, and then we have a second derivative that is negative. That means concave down. So with that being, so it's increasing concave down. That's going to look like this. Okay. I'm sorry, increasing. That's decreasing. Increasing concave down would be like this. Concave down, I'm still dumping water, but I'm also increasing, meaning like the derivative at every single point is going to be positive, meaning the slope of your tangent will be positive. And last one for our notes today, and I hope you guys are keeping up with the notes, otherwise pause it. take as good notes as you possibly can because we are going to be assessed on this on Thursday/Friday, which is day 2 of week 6. Now we have a decreasing function. And we have a concave down. So decreasing concave down would be like I did before. Actually, it's like this. Okay, so there's our tutorial on the relationships of increasing, decreasing functions with the first derivative, and then also how to use the second derivative test to determine whether something's either a max or a min, or whether it's concave up or concave down, and also what those functions could look like. If I went too fast, please pause the video and look out for your assignment. You guys have a wonderful day. Bye.